Hello and welcome to CMG's webinar on reduce economic risk through accurate lab to field scale chemical EOR simulation. My name is Anjani Kumar. I'm the Vice President of Engineering Solution and Marketing at CMG. I'll be the moderator for today's session. I'm pleased to introduce Fraser Skoreko, Chief Reservoir Engineer at CMG, who will be presenting today's webinar. Fraser has over 35 years of industry experience and has been with CMG since 1993. He specializes in advanced EOR processes like chemical EOR, foam EOR, in-situ combustion, and other advanced recovery processes that require advanced reservoir simulation technology. Fraser graduated with an engineering degree from the University of Calgary and started his career as an open-hole logging engineer in 1978. He then moved on to work as a reservoir engineer at Gulf Canada Alberta Energy Company, currently known as Encana, and has worked as an independent consultant at various places internationally for several years. At this time, I'd like to inform you that there will be a question and answer session at the end of the presentation. However, you may submit your question at any time during the session using the chat window on your screen. We will also be recording the presentation and will be posting it on our website within the next 24 hours. You may log in using your CMGL username and a password to access the material. Also, I'd like to inform everybody that we do have our newly redesigned website active since yesterday, and there's a lot of material, self-learning material on our website available. All of our previous recorded versions of the webinars are also available if you want to reference it at your own time. Over to you, Fraser.
All right, thank you, Anjani. Welcome to the webinar on accurate chemical EOR simulation lab to field scale, and we'll talk about things like salinity gradients, saponification, and geochemistry. So the outline is, first of all, why use GEM for ASP. I'll talk about some ASP mechanisms such as saponification, salinity, interfacial tension, relative permeability, and then I'll do a live demo followed by a conclusion. So first of all, what is ASP? This diagram is just showing what might happen in a typical ASP flood, where you have a untouched oil zone ahead of the front. You might have a pre-flush zone that's been flushed by seawater, for example, for many years. Then you have the zone where the chemical flood is done, and you have your alkaline surfactant polymer chemical cocktail there. And one of the main mechanisms is where the alkali reacts with the acid that's in the oil to form an in situ surfactant. And we call that in situ surfactant soap so that we don't confuse it with the injected surfactant. And then that's followed by a polymer flood for mobility control, and then a final water flood. So why use GEM for ASP? First of all, we need to achieve optimum conditions by maintaining a strict salinity gradient during the flood, and field and lab tests have shown that you could get process failure if you do not adhere to that strict salinity gradient. So the GEM method is just accurate ASP process modeling with salinity gradients in a full field 3D model to hopefully prevent any costly failures. And it is the only commercial simulator that models ASP with soap and salinity gradients in a 3D field scale model. So now a little bit about mechanisms. This diagram is just showing your typical desaturation curve. We have residual oil saturation here on the y-axis and capillary number on the x-axis. And as we increase the capillary number, our residual oil saturation decreases. Now, since the capillary number is given by viscosity times velocity over interfacial tension, we only have so much control over the velocity and viscosity, so it's the interfacial tension that we're targeting with chemical floods. And we also get wettability changes during a chemical flood. Now a little bit about saponification, or the creation of soap in situ. The main point of this slide is to point out that the quantity of saponification that occurs is dependent on the oil saturation. So the diagram is showing kind of a typical flood where you have an untouched oil zone that has high oil saturation and high acid, and then as the flood progresses you get lower and lower oil saturation and also lower amounts of acid. So as I mentioned, the amount of saponification is dependent on the oil saturation or water-oil ratio. And then at the bottom is just a typical reaction that might occur. The oil with carboxylic acids plus the alkali gives soap. So that leads into this slide here, which is showing a typical activity diagram. And what we have on the y-axis is essentially salinity. It's our alkali concentration, but you know, the alkali has sodium, so there's salinity associated with it. So it's salinity here, and on the x-axis is concentration of oil over concentration of surfactant. But just to simplify things, let's think of it just as oil saturation. So oil saturation is increasing to the right and decreasing to the left. Now also what we have on this activity diagram is this yellow zone, which is our type 3 emulsion phase. And that's where we want to be. That's where we get our ultra-low interfacial tensions. We also see that there's this negative slope. And the reason for this negative slope is because typically the soap has a much lower optimum salinity than the injected surfactant. So on the right side of this diagram, you know, you have high oil saturation, so high amounts of soap. So the soap is dominating the system and the optimal salinity is quite low. On the left side, the oil saturation is low, so the surfactant is dominating it and you have a much higher optimum salinity. And that's one of the main reasons why we need a salinity gradient with ASP floods. We need to stay within that yellow region. Now this next slide is showing some results from this SP paper that I thought were quite interesting. It investigated 3 different surfactants. Now for each surfactant there's an activity diagram on the top, and then on the bottom is the corresponding solubilization ratio plot. Now the IFT equals a constant over the solubilization ratio squared. So we can think of it just as the IFT is essentially 1 over the solubilization ratio. So providing the solubilization ratio, the optimum, which is a crossover point, providing that's over 10, then we have, you know, quite a good IFT reduction. So with this surfactant number 1, you can see that there's quite a steep slope of our type 3 microemulsion phase here, and then it's gradual here at higher oil saturations. You could imagine field operations might be quite difficult with this surfactant. Trying to maintain, you know, everyone in the reservoir within, you know, this with this range here, with this steep slope, it becomes quite difficult. So because of that, they changed the surfactant formulation and moved to surfactant number 2 here to try to rectify that steepness. And you can see that they did succeed at the low oil saturations, but at high oil saturations it became steep again. So it wasn't quite perfect. The solubilization ratios, again, are quite good. In fact, all 3 of these surfactants give quite good IFT behavior. Now, so then they moved to surfactant number 3. They changed the formulation again, and this time they're quite successful. You know, you can see here that the slope of the type 3 curve is quite gradual. So it's saying that the properties of the surfactant were quite similar to the properties of the soap, and you have a very gradual slope here, so field operations are much easier. Now for systems with no alkali, some light oils have a very low acid number. In that case, you may not want to, or you may not need to inject alkali. You can provide salinity with just salt. So for those systems, you might want to just inject surfactant, or maybe surfactant with polymer, or perhaps a foaming surfactant. But even for systems like this, you still need a salinity gradient. And this diagram is trying to explain why that is. Now, what you typically would do is, first of all, inject at a higher salinity than your optimum, and then follow that with your optimum salinity. And the idea there is to try to make sure that every point in the reservoir goes through the optimum salinity, because you cannot always predict exactly how much losses you might get of the surfactant due to absorption and perhaps other losses. So that ensures that everywhere is going to go through the optimum salinity. Now the diagram here is just showing what the IFT may look like for these different zones. So at the higher salinity than the optimum, the surfactant will partition more into the oil, and that will tend to focus the surfactant near the front here, at the front of the optimum salinity. And then you follow that, the optimum salinity, with a lower salinity slug, and there's two reasons for doing that. The first reason is to make sure that the surfactant is in the same phase as the following polymer flood. And the second reason is because polymer is more efficient at lower salinity. So the ASP history in CMG, many of you may know that STARS has been kind of the standard for many years, 16 plus years. But more recently, lab studies and field studies have shown that more mechanistic modeling of ASP is required. The salinity gradients are very important. Now, some chemical flood simulators model the microemulsion phase as a separate phase, but these simulators are either not commercially available or cannot model full field 3D problems. So because of all this, the knowledge gained for many years with STARS has been applied, upgraded, and installed in GEM. Now, of course, many may wonder now when you should use GEM, when you should use STARS for chemical EOR. So these are detailing our current recommendations. So first of all, for ASP, a salinity gradient is required, so the choice should currently be GEM, because you can model saponification, salinity gradients, and microemulsion viscosity. So with GEM, the emulsion is distributed between the oil and water phases using the solubilization ratio curves, and you don't need a third liquid phase. The modeling of a salinity gradient for ASP is currently unavailable in STARS, but will be available soon. For surfactant polymer or surfactant with foaming capabilities, both simulators can model salinity gradients. So then a choice becomes dependent on the oil type, or if there's other EOR processes to be considered and compared. Now, for light oils, where miscible floods or other compositionally complex processes may be investigated, an equation of state is the best way to model this, and the choice should be GEM. If the microemulsion viscosity is important, then the choice should be GEM. For heavier oils, or if steam injection processes are to be considered, or more complex behaviors to be modeled, such as fines, plugging, microbial, many different types of things. STARS is quite flexible in that regard. then stars should be the choice. Now for alkaline surfactant with foam or surfactant with foam with mobility control and IFT reduction, the choice should be GEM. And that's because the GEM's foam model, it doesn't need rel perm interpolation. And therefore the rel perm interpolation can be used for IFT modeling. Now a little bit about GEM and how it models it. As I mentioned, the microemulsion phase behavior is modeled with 2 liquid phases and no separate third liquid phase is required. So it's the microemulsion phase behavior is handled by partitioning this phase between the oil and water phases according to a principle of controlling the IFT. Now this equation here is showing one of the equations. So the oil and water IFTs are averaged to compute the IFT using a weighting factor. So this weighting factor gamma is the important one here, and it's given by the volume of oil in the microemulsion phase divided by the total volume of the microemulsion phase. Now the partitioning is also handled using this gamma factor, and so the volume of surfactant in the oil phase is this gamma times volume of the total surfactant, and similarly volume of surfactant in the water phase is 1 minus gamma times the total volume. We also have viscosity increase capability due to the microemulsion phase, and that's using a special viscosity calculation of this form that you see below here. For example, log of the oil viscosity is a function of the gamma times log of the microemulsion phase viscosity plus 1 minus the function of gamma times the log of the oil viscosity. And then similar thing with water. Now a little bit about the IFT input and how we handle it. This diagram is showing a typical plot of IFT versus salinity, and it's at 2 different surfactant concentrations and 3 different water-oil ratios. So you can see that at the low surfactant concentration there's not too much IFT reduction. The curves are all up here. With the higher surfactant concentration, you get some quite good IFT reductions. The curves are down here at very low values. And we can see also 3 curves corresponding to the 3 different water-oil ratios. So you can see the shift in the optimal salinity. At a water-oil ratio of 0, the optimum salinity is around 15,000. And then as the water-oil ratio increases, we see a shift to the right of the optimal salinity. Now in GEM, the optimal salinity table is input as a function of soap over soap plus surfactant ratio. An example is given here for the same data that we saw on the previous plot. We see that there's 2 different tables required, one for each surfactant concentration. Now here's a different plot of the same data. It's as I mentioned previously, the IFT is just equal to a constant over the solubilization ratio squared. So it's essentially the same data, IFT, but then just plotted as solubilization ratio. And we can see again with our 3 different water-oil ratios, our shift to the right as the water-oil ratio increases. So now I'm going to start a live demo and show you how things are input, and hopefully things become a little bit clearer when I do this. So what I have here is a data set loaded in Builder. It's Builder 2016.11, and it's a simple data set of a Coreflood, just 101 blocks long, one-dimensional, and quite a simple fluid model, just one oil component representing the oil. So I'll start the process wizard, and we have two options here, either ASP or foam or low salinity. So we'll select the ASP option here, click Next. Then we have some inputs required for ASP, and what we have here are a number of different choices for either ASP or surfactant or foam. So we'll select this one here, which is the full ASP, and we get this message. And this message is just telling you that you need a special version of GEM. These capabilities are not in the release version that everyone has, but all you need to do is ask CMG and we will provide this version for you. And it'll run with the same licensing that you already have. So now we can see that there's some inputs here for the wizard, color-coded. So the top blue ones are the inputs required for polymer. We have polymer, whether it's a function of salinity or not, some polymer absorption options, and then whether the polymer degrades with time or not. Then this sort of purplish color here are what to do with rel perms. Now, the default number of rel perm sets will be 3. So typically, the last one will be the straight line theoretical miscible curves. The first one will be the normal reservoir flow, the ones that were provided in the data set. And then it'll be set number 2 that we normally use for matching Corefloods for tuning our ASP data. So you can see that most of these options are designed what to do with set number 2. So how to handle the SORW reduction. So the default in the wizard is to multiply SORW times 0.5. It's designed this way because, as you can imagine, many data sets may have hundreds of rel perm sets, so we need a method to be able to handle many rel perm sets simultaneously. Also, how to handle the KRW change. We normally want to shift to be more water wet, so the default is to multiply the KRW at residual oil times a factor of 2. Now, of course, you can change that if you want. And then also, if you want to change the capillary pressure, normally with shifting to be more water wet, the capillary pressure is reduced. So you might want to reduce those somewhat. The default is 1, not to reduce it. And we're going to just accept the defaults here for this example. The green color here is for absorption, whether to use it or not. And then at the bottom is whether to use saponification or not. And if you are using it, then you need the oil acid number. Now the wizard will calculate the mole fraction of acid required for GM input from this acid number. So I'll click Next now. And now we'll get to the geochemistry input. And as you can imagine, geochemistry input can be a bit complex. So we have some defaults set up to sort of help the users decide what to use. So we have a few defaults, for example, minimum components for sodium hydroxide or sodium carbonate. We have defaults for clastics and carbonates with and without ion exchange. So for this example, we'll just use the minimum components for sodium carbonate. Once we click that, we get these aqueous reactions. There's 3 aqueous reactions. We got no mineral reactions, and we got 1 ion exchange reaction. Now for this example, we're not going to use ion exchange, so I'll just uncheck that. This example also has some consumption of the alkali during the Coreflood. So to try to account for that consumption, we'll use a mineral reaction here of calcite. So we'll just add this here. So now we got one mineral reaction here of our calcite. Now if you wanted to add other reactions, you can very easily do that in the wizard here. You can click here and you can select from a short list. If you want the entire list, you just check this box here to show all reactions. And then you have the entire reaction set that are in the chemical database. So normally that's too many, so that's why we have this short list here. So now we need some data input for the initialization of GEM. So I'll input a pH of 5. Now GEM does not require a pH input. It requires an input of the hydrogen ion. So the wizard is just going to calculate the hydrogen concentration from this pH that we input. We also need HCO3. We'll use 200. Now for sodium, we'll use 50,000. Now for this particular example, we're using just sodium to model the salinity. Now we could select any ion we want. Multiple ions. We could select sodium plus calcium or sodium plus chlorine if we want. It's entirely up to the user. This example will just use sodium. And then for our calcium, initial concentration is 2,000 ppms. And our calcite volume fraction is 0.1. So now we'll click Next. This is just showing what components will be added to the oil components. So we'll just accept defaults, click Next. Here is where we're selecting the rel-perm regions to apply it to. As I mentioned, you may have hundreds of rel-perm regions in your data set. You may not want to apply it to all of them. Anyway, in this data set we only have one, so we'll select one there. Now we come to the IFT input panel, which is kind of important and a little bit more complex. Now for this example, we also have some lab data. So let's first look at the lab data here. And what we have is we have IFT versus alkali concentration here. You see here this mentions here what it is. This example assumes it's variable alkali concentrations injected with a constant water composition. So that's what we have in our table here. So we have two different water-oil ratios, and we have two different surfactant concentrations, surfactant of 0 and surfactant of 0.11. And our injected water composition is 6,000 ppms. So now let's go back to the wizard, and we'll change our input data so that we can accept that data. So first of all, because we have multiple water-oil ratios, we need to use this last option here for inputting the IFT. So it's at multiple water-oil ratios and surfactant concentrations. So once we select that, now we have input for water-oil ratios. So let me just change this. The wizard supplied us with 3 surfactant concentrations by default. And you can see down below that they're plotted IFT versus salinity for the 3 different surfactant concentrations. You can also notice that the salinity starts at 10,000 ppms. Now that salinity, it's calculated from our injected water composition and our alkali. So at 0 alkali it's 10,000, and that's because that's the default, and I'll show you that in just a moment. So I'll change it to be just 2 surfactant concentrations of 0 and 0.11. So our plot changes once I do that. Now if I click here, this is just showing our default injected water composition. So it's default of 10,000 ppm sodium, and we're injecting sodium carbonate. And we're only using sodium for the salinity calculations. If we wanted to use both sodium and calcium, we just check both of them here. Now we just go back to our lab data for a moment. We can see here our injected water was 6,000 ppm salt. If we calculate the sodium fraction of that just from the ratio of molecular weights, our sodium fraction is 2360. So let's just input that number here. And we'll click OK. And now we can see our plot changes to start at 2360 ppm salinity at 0 alkali. So the only other thing we need to do now is to change our water-oil ratio so that we have our two input values of 1 and 10. And now we're ready to copy across our lab data. So let's copy the IFT data here for water-oil ratio of 1. And we'll paste it into our table here. And then we'll do the same thing for a water-oil ratio of 10. And we change it here to be water-oil ratio of 10. And we paste it in here. So now we can see that our lab data is now plotted here as these points, but GEM is not really matching it. Now what we need, because we're using multiple water-oil ratios, we need to use this optimal salinity versus soap over surfactant ratio. So I'll just check that. And what we could do, I mean, we're not matching our lab data. You know, GEM is just showing these solid straight lines here. And that's because our optimal salinity table is not calibrated yet. So we could just click here and input some numbers manually. But fortunately, we have a button to calculate it automatically. Just click that, and now we match our lab data quite well. Lab data at the high surfactant concentrations for the two different water-oil ratios. So we see here we have a nice shift of the optimal salinity at our lowest IFT, have a shift with the increase in water-oil ratio. So now we're essentially finished with our IFT input, but before we go, we can look at some other plots. We can look at, first of all, IFT versus alkali. So the x-axis essentially just changes to be the alkali concentration, essentially what is in our table here. Or we could look at the solubilization ratio plot, and then we just have our optimum salinity points where the two lines cross here and here. So now we can click Next and go on to the next step, which is our absorption input. We have absorption for surfactant. We have absorption for polymer. We could input our tables of data. For this example, we'll just accept the defaults. Click Next. Here is where we have polymer input. Polymer input can be a little complex depending on your data. If we had selected polymer as a function of salinity in the first panel, then we would have that come up here as an option. We could input data as a function of salinity. We can also input it to a function of velocity or shear, or all salinity and velocity or shear together. For this example, we're just going to accept defaults, but it essentially works the same way as the IFT input, where you input your lab data here in the table, and then you select the options so that you match the lab data as best as possible. So we'll just click Next to select the defaults. And now here is where we input our injection water compositions. For this example, we're injecting 500 ppm polymer or 0.05 weight percent. So I'll input that. Our surfactant concentration was 0.11 weight percent. Our hydrogen concentration was calculated from our pH input. We could change it if we want. We'll leave it as the default here. Our sodium concentration was, it's put the same as our injected water in the lab, but we could change it here again. And then our alkali injection, which is this one. This is the NaCO3 is the aqueous form of our alkali. So we'll just input a value here of 768 ppm of our alkali. And we'll just select this date of the injector, which is when we inject our ASP slug, and click Finish. So now that we've done that, we can look at what we got from the wizard. First of all, we'll look at our rel perms, what the wizard gave us. So the wizard added 2 additional rel perm sets. So what we started with was this rel perm set here, our normal reservoir flow. Then the wizard added rel perm set 2, where we multiplied the SORW by 0.5. We see this shift here, the SORW times 0.5, so we see this magenta curve shifting because of that. We also see a shift of the KRW. Now remember that we multiplied the KRW at residual oil by 2. Now it may not be totally obvious from this plot that that's what's happened, but if you look at it in detail, it's because there's 2 things going on. We're seeing our SORW is shifting. Now remember, we're multiplying the KRW at SORW times 2. So originally, our KRW at SORW was this value, and now at our new SORW, it's this value. So you can see it actually is multiplied by 2. It's just a little bit deceiving that the green curve is to the right of the red curve here. And then our set 3 is our theoretical straight line miscible curves. Now we can look at some other data that the wizard supplied us. If we look at the actual keywords, you can see that the wizard added 2 oil components, which is our acid and our surfactant. Then the wizard also added our solubilization ratio data, which is, I guess, the most important. So it added actually 2 tables, one for each surfactant concentration. So the first table is for surfactant concentration of 0. Second one is the more important one at a surfactant concentration of 0.11. For each table, we also have a table of our optimum salinity versus soap to soap plus surfactant ratio. There's 2 tables corresponding to each solubilization ratio table. Also, the wizard added our aqueous components, added 9 aqueous components. We also got 1 mineral component and our corresponding aqueous reactions. We also got a reaction of our soap creation, so the acid in the oil equals the hydrogen, which is essentially acid, plus our soap. And we also got our polymer data, polymer viscosity data here, and this is showing that we're only using sodium for our salinity calculations. So now I'll move on to actually using this data. So once I created this data in the wizard, then I put it into CMOST, and these are the variables here that the parameters in CMOST that I use to match the Coreflood data. So there's 12 different parameters that I used in CMOST. So the first one is the acid to soap reaction rate. That's going to affect alkali production. Then the rel-perm interpolation value of the capillary number, that'll affect oil recovery. Intercomp valve 3 is normally not used. The KRO and KRW endpoints, that's going to affect delta pressure when SW is low or high. Polymer absorption will affect polymer production. The residual resistance factor will affect delta pressure. The SORW affects oil recovery. Surfactant absorption affects the surfactant production and oil recovery. This top cell X is our solubilization, the optimum salinity versus soap to soap plus surfactant ratio. It's going to affect the oil recovery behavior as a function of salinity. The viscosity of the polymer will affect the delta pressure. And then the viscosity of surfactant here, it's the microemulsion viscosity that'll affect delta pressure during ASP injection. Now if we see the results, we saw that we got, actually first of all I wanted to show the actual CMOST results here. So we see we did 170 some runs, and we got a fairly good match after 136 runs here. So now if we just look at the results here, so the optimal case, the match case, is the red one, and then all the light blue ones are the many different cases that were tried, the points being the lab data. So this first plot is the alkali production. There was 2 slugs of ASP during this Coreflood. The second slug was twice the alkali concentration of the first slug. So we see here we didn't see too much alkali consumption during the first slug, but we saw some during the second slug, and we matched that fairly well with CMOST here. The plot here is the surfactant production. It's kind of an interesting plot here. What we see is that the lab data is showing a ramp up of the surfactant concentration, and then we see here a spike of the surfactant production, followed by a tail off. Now, this spike is caused because that's exactly when the alkali injection stops. So the spike is caused because, remember, the surfactant will partition into the oil at high alkali concentrations. So during ASP injection, our alkali, our salinity is fairly high, so it's partitioned into the oil. Once we stop ASP, the salinity drops and it'll partition back to the water right away. So that's what causes this spike here. So we can see we got a reasonable match of the surfactant production, and I did some fine tuning of this match that I'll show in the next slide. And then on the second slug, we see a lower surfactant production that we're able to match reasonably well. And then down here is our delta pressure. We got quite a good match of delta pressure, and cumulative production was matched quite well. Now this is just showing the fine tuning I did. Now I changed the absorption and the optimum salinity table, and I got a much better match of this portion of the curve, showing that that GEM is matching the phase behavior fairly well of the surfactant, showing that as soon as we stop the alkali injection here, which is the green curve here, we get this spike in surfactant production that we are matched fairly well. The only part of the curve that is not matched that well is this ramp up here, and that ramp up could be matched possibly by changing the input solubilization ratio curves. Now remember, in GEM, the phase behavior of the surfactant is controlled by the solubilization ratio curves. Now in this example, since we used a constant IFT input from the lab, didn't really change those curves. So that's why we don't see a good match during this ramp up, but I'm fairly sure we could get a better match if we change that input IFT data. Now if we take that lab data and we upscale it, now I'm not going to go into the upscaling techniques during this webinar. It's almost a subject in itself and will require quite a bit of time. If anybody's interested in that, they can contact us and we can deal with that. But anyway, so the Coreflood data was upscaled and then it was put into a field scale inverse 5-spot model. And I did a CMOST optimization of oil recovery. Now I could have done a optimization on net present value, but for this example I just used oil recovery. We didn't have a lot of cost information for a net present value type optimization. So we have 3 different salinities. So salinity of the initial ASP slug, salinity for the ASP slug after 5 years, so an intermediate salinity change, and then a salinity for the post-ASP polymer flood that starts at 10 years. We also have polymer concentration for the ASP slug and polymer concentration for the post-ASP polymer flood, also surfactant concentration. So once we see the results from that optimization, we see here that what we started with was this black line here, the base case, and our optimized case was the red curve here, and we see quite a good increase in recovery. Right at the very end, it's an increase of about 3% of the oil in place, and that in itself would represent quite a good increase in revenue just from doing an optimization like this. And if you look after 10 years, you see quite a huge difference in the recoveries, over 10%. So that would represent quite a large revenue difference between the cases. So well worth it to spend a small amount of money to do an optimization. Now here I have some movies. It's a slightly different field scale model, but just to illustrate that that GEM does fairly well with field scale problems. This is 4 inverted 5-spot patterns, and it's seawater injection at 2015, ASP at 2035, and then some changes of salinity. So we have 3 movies. We have salinity on the left, oil saturation in the middle, and soap fraction on the right. Now soap fraction is not going to change until ASP starts at 2035. Soap fraction will essentially be our microemulsion phase. So I'll start the movies now. And we can see during seawater injection, our salinity is dropping due to the seawater. Our initial salinity was quite high. Our oil saturation is decreasing due to the seawater flood. Then at 2035, our ASP starts. We start to see our soap being created. We see our residual oil, or our oil saturation dropping to very low values, and some changes of salinity as we change salinity and do our final polymer flood. The total flood goes to the year 2015. So in conclusion, I'd like to point out to begin with that because of the way GEM is structured, you can simultaneously model in one data set low salinity and miscible CO2 or hydrocarbon miscible and foam and ASP all together. So you don't need to change simulators to compare processes. So GEM is really the best choice for ASP. It can model salinity gradients, saponification with ASP in a 3D field scale model. It can also model foam with alkaline surfactant. And no other commercial simulator in the world can do all of this.
Thank you, Fraser. We will now take up questions. If you have any questions and have not already submitted it, you can use the chat window on your screen to send us questions. I see there are several questions already in the chat window here, and I'll try to take them one by one. The first question is by Thomas Ravenstein, and the question is, when core flooding with only polymer, no ASP, what parameters are advised to history match, and is STAR sufficient for this type of modeling?
Okay, the answer to that one is either simulator is good for polymer simulation, either GEM or STARS, and most likely the way you would want to model it is with the viscoelastic effect. Kind of the more recent developments are showing that you can model that with a capillary number change. So you would set up your rel perm interpolation as a function of capillary number and tune that to your lab data.
The next question is from Alireza Bigdaily, and the question is, at the geochemistry section, is it possible to couple GEM simulator to other geochemistry simulators such as FreakQC?
That's not required. GEM has the geochemistry implicit built right into the simulator, so it's very, very fast and robust. I mean, when you couple to FreakQC, reports are that it becomes very, very slow when you do that. So GEM's geochemistry portion has been calibrated to FreakQC and a few other geochemistry simulators, so they do produce the same results, except GEM is just much faster.
The next question is from Jiho Lee, and the question is, does GEM consider pH-dependent adsorption of surfactant or salinity-dependent adsorption of polymer like STARS?
GEM does not do that yet. It is on the list to do, but we recognize that probably the pH dependency is probably the most important one.
The next question is from Mustafa Husseini, and the question is, why did you use several water to oil ratio? Why not use only one water oil ratio, and how do we know which oil water or water oil ratio to use?
Well, the reason for using multiple water oil ratios is because the behavior changes with different water oil ratios. So your optimum salinity will shift, and that's how you end up with those activity diagrams that I was showing. So you have that negative slope with your oil saturation change. So it's very important to model that properly so that during your field operations you can maintain your salinity in the optimal salinity range. As your water oil ratio changes throughout your flood, you'll need to change your salinity.
So the next question is from Ralmi Espianza, and the question is, can GEM handle dual porosity mode with its new features in chemical EOR? Can GEM handle dual porosity mode with its It's basically the same question by two people.
Yeah, I mean, GEM handles dual porosity or dual permeability. We also have our subdomain methods. I mean, all those methods are available with anything else, with foam or with ASP, whatever.
The next question is from Gaoming Lee, and the question is, I thought you entered the IFT table, but in the data file, it was converted to solubilization ratio. Can you just enter solubilization ratio in the wizard?
In the wizard, that's something that we're going to put in the wizard just to enter the solubilization ratio tables directly. But I mean, right now the wizard doesn't have that, but you could very easily just enter your solubilization ratio tables directly into GEM.
The next question is from Hamid Al-Lashgari, and the question is adsorption model reversible or irreversible, and is a function of pH, yes or no? Is adsorption basically the same question? Yeah.
Yeah, adsorption can be either reversible or non-reversible. It's up to the user to choose. And as I mentioned, the absorption is not pH dependent yet in GEM, but it will be very soon.
So the next question is from Raul Moreno, and the question is, why do we match for optimal salinity with water-oil ratio? Why not SORW or SO?
Okay, I'm not sure I understand that question. I mean, it's SO is essentially the same as water-oil ratio. So I mean, we match our optimum salinities to water-oil ratio, or SO.
We can take this discussion offline with Raul on this particular question.
Yeah.
So let's move on to the next one, and the next question is from Carlos. Can GEM track the movement of microemulsion as it moves through the reservoir?
Yes, it does track it. You can, you know, in that movie that I showed, it's showing the microemulsion phase, or the soap, as it moves through the reservoir, and you can plot it. You can also plot the viscosity change due to the microemulsion phase.
The next question is from Richard Morera, and the question is, does temperature affect chemical equilibrium processes, and how do I use temperature in GEM?
The temperature does affect all the equilibrium reactions, and those are built into GEM. They're built into the database that GEM uses. Now, to actually model that in GEM, you need to turn on the thermal equation. So I mean, it's not on by default, but it can be very easily used. So the answer is yes.
Now, it looks like there are several other questions in the chat window. There were around 500 people attending live on this webinar, and I still have like 50 more questions to take on. But do keep on sending the questions. Unfortunately, we will have to stop the question and answer for time's sake here. And we will get back to you individually with the answers to all of your questions within the next day. So please do not feel that we did not pick your questions. It's because of time constraint, I'll have to stop the question and answer session at this point of time. So I hope you have gained a better understanding of the mechanisms involved in modeling of chemical EOR and the various features and capabilities of CMG simulators to model advanced chemical EOR processes. CMG does offer a lot of training courses for various skill levels on chemical EOR and a variety of other subjects at training centers around the world. We also offer company-specific customized courses at company venues. If you are interested in customizing the courses for your needs, do let us know. I'd like to invite you to visit our website to look at our training course offerings, which are detailed on our website. We will post today's recorded presentation on our website within the next 24 hours. You'll have to use your CMGL username and the password to log in and access the material. If you have any other questions, then feel free to send us an email at sales@cmgl.ca, and we'll be more than happy to answer your questions. Again, thank you for joining us for today's webinar on reduce economic risks through accurate lab to field scale chemical EOR simulation. Thank you.